So, hey boys and girls, welcome to Munro Live. I'm here with Paul, and we're standing in front of the new VW electric drive system, and I'd like to thank the people over at VW for giving this to us. It's not given. We're borrowing it so we can take it apart, have a look at it, and I think you're going to be very excited about what Paul and I have to say.
Yeah, we're really excited to see it.
Hey boys and girls, I'm here with Paul, and Paul is one of our experts on electric motors. So I'm going to be taking kind of the back seat a bit because he's taking it apart, and Paul really is an electric motor kind of engineer. So we're going to go through the VW electric motor here. And quite frankly, I will tell you, when I did the first VW motor, I was very impressed, but now I'm uber impressed.
They've stepped it up a notch.
Yeah, there's no question about it. So let's talk about the highlights first. Maybe you can touch on some of these things.
So one of the key things, and I got it down here fourth, but this whole thing fits in exactly the same package as their old one.
Yeah.
And yet it produces 560 Newton meters of torque, which is a lot more than the 310 from the original, and 210 kilowatts of power, a lot more than 150 kilowatts.
Right.
So right away, as you drop this into every one of VW's vehicles, it's going to dramatically improve how fun it is to drive and make VW's electric vehicles much more competitive. And the main thing that they did with this, the whole goal, was improved efficiency. And you can see it in every part that they put in.
Yeah.
And so that improved efficiency is going to result in longer range for the same battery, or allow them to go to less battery for the same range. And so it's going to pay dividends for VW. I'm thrilled to see it.
So let's just hold on to that for just a second. Okay, so I have thrown quite a few rocks at VW. I'm not going to go over them. But I did like their electric motor, the last one. Mm-hmm. So I said that this is uber better, and you just heard the outputs. And it's in the same package. Okay, so this, as far as I'm concerned right now, is the second best electric motor on the planet. I love the Lucid. They've got a technique that made it smaller and more powerful and all this other stuff. But at the end of the day, only Lucid could use it, and they're not a growth company. This is going to make a big difference for VW. I think this is going to. So I may have to suck back some of the stuff I've said about the ID.4 and the ID.3. I'm telling you, I'm really impressed. So let's go in and talk about the similarities to the Ford Lightning, because instantly this kind of looks the same.
So the Ford Lightning has almost exactly the same stator winding, and the size and torque of the motor itself and power are very close to the Ford Lightning, and that does put it in the top 10 of power density, torque density in the world. You did mention that Lucid's number one, but there are sacrifices when you do that sort of thing.
Right.
Go to extreme small package size, and VW chose deliberately to go to a larger motor and spin it slower to get higher efficiency over the overall system.
Yeah.
And so that's, again, the winding itself is not super innovative, except in the execution of the winding.
This is what I was really impressed with, these bumps.
And the uniformity of the hairpins and the spacing between them is spectacular. And that kind of thing leads to durability. I spent tens of thousands of hours doing durability testing on electric machines. And you get to the point where you can see right away the kind of machine that's going to do well on durability testing. And this is the kind of thing you like to see.
So let's talk about the output that you got here, because that totally blew me away. No variation on an electric motor.
Yeah, that
blew me away.
So it just goes to the core of every aspect of this motor. We did measurements on the resistance of the windings. So from phase to phase, there are 3 phases in the motor, 3 connections, and you measure the resistance from one phase to the other and then see if it's balanced. And typically you like to see balance within 10% or better. But of course on the VW motor, it was 10.0 milliohms for the first phase, 10.0 milliohms for the second phase, and 10.0 milliohms for the third phase, precisely balanced. And exactly, it's one of those things that you know that the original target of the design was to hit 10.0 milliohms on the phase-to-phase resistance. And so they build the first prototype, and there's all kinds of things that happen from testing and the discovery process, and then through manufacturing, and the people are building the tooling to make the winding, and there's a lot of compromises over a period of years to get the final product. This is the end of the machined and manufactured product off the end of the line, and to have that still be exactly what the original intent was.
Yeah.
Somebody shot an arrow at a target on the moon, and 2 years later when the arrow hits, it's in the dead center.
Yeah.
And you see that kind of quality craftsmanship all the way through. And it's a team effort. You can't do that. Just one person can't do that by themselves. It's the machining people on the line, it's the quality control, it's the people in purchaching. The whole team working together is what it takes to deliver this kind of
So
build
let's
quality.
talk a little bit about how hard this is to do. I don't think we've seen one where it's exactly the same on all 3 phases.
Right, usually there's a little bit of difference, one phase to the other.
That's number one. To do that, see these copper windings here? Okay, this copper is kind of expensive. There's always a purchasing agent that says, hey, I can get us some cheaper copper. And as soon as you do that, you bugger everything up. But there's one thing we forgot to mention. This pipe with the stator in it goes inside this little hole, okay? And what I'd like to do is just touch on the fluid here, because fluid is a huge deal when you're trying to cool electric motors and whatnot. And Ford uses one technique, but these guys use a different technique that initially I was surprised at, but now I'm delighted with.
Yeah, so it is a unique hybrid combination of water cooling and oil cooling for this motor. So they have water cooling on the stator with this inner housing going into the main housing, forming the water passages and big O-ring seals to keep the water in place, because obviously you don't want water ever getting close to the high voltage windings. So they do that to cool the outside of the stator, but the inside is cooled with oil spray. And let's get to talk about the rest of the system to see how that oil spray ends up working.
Yeah, we can get to that later. I just wanted to make sure that people know that this going inside here, okay, so I'm a tool maker. I don't do much of that stuff anymore, but I know how hard it is to make something round. It's very, very difficult, especially when you're looking at a pipe like this. Okay, so centerless grinding and all these different techniques and tricks that you can use. This is not centerless ground. I can see the little bumps here. This means it's machined on something like a lathe, maybe a bullard, I'm not sure, but this has to be absolutely phenomenally accurate, and so does that. Because like Paul just said, no water, we don't want any water going anywhere. This, to me, this accuracy that they've got between here, there, and of course the stator itself, this is actually freeze fit. But at the end of the day, this shows German engineering at its best. Like I said, I'm going to be a little gushy on this. I really like the way this is going.
Yeah, this is the kind of thing that gets us excited because you don't see a typical outfit that's. We get a lot of teardowns. We've done a lot of motor teardowns.
You can see them in the background.
There's one trend that's happening today is kind of a race to the bottom. You know, how do we make the cheapest, barely adequate motor? And this is going the other direction, and it's one of the things that you like to see because it's the system level that is the king. That if you can improve this and get money out of the battery, or get the most mileage out of the battery you have, then you win in the end. Most of the industry, the direction is go to higher and higher gear ratios, spin it faster because the output torque here is what you really want going to the wheels. And so if you have a really large gear ratio, you can make the motor smaller and lighter and cheaper. As you go that direction, the motor starts to sound like a dentist drill. And so what they've done, the other thing you do is you gain efficiency in cost, but you lose electromagnetic efficiency when you go to that high speed. And so what they've done is slowed things down a little bit, and they've gone to a 9.8 gear ratio from the 13-to-1 gear ratio. And so they're spinning this a little slower, which makes it more efficient. The lower frequency makes things more efficient. And then this thing has to handle huge torques, but it does so with amazingly low friction. They've optimized these bearings and the finish on the gears and the spacing of the gears so perfectly.
Let me just move this in so you can see what's going on here. Yeah. This isn't just a simple gear set. Well, it is a simple gear set, but at the end of the day, you've got one of your input shafts, and then you're going to
the lay shaft,
and then you're into the drive.
This is the differential.
Yeah, the differential drive. So, but this is something you can't do with anybody else's out there. Watch this.
It just keeps spinning.
Are you kidding me?
Right.
This is just absolutely brilliant.
And so it's built like a Swiss watch, although in Detroit we say built like a Shinola watch.
Okay, good. Yeah.
But yeah, it's amazing the quality of and the low friction of the gear ratios. I did another video to talk about these roller bearings. So just the choices that they made, moving the lay shaft. Typically you would like to have a lay shaft down here where the oil level is going to keep it all lubricated. So in an internal combustion engine, that's how you do it. It's easy to lubricate that way. Yeah. But that ends up stirring up the oil and creating more loss.
Well, it creates a milkshake as well, which is not good for lubricity.
Right, and then they've moved that up out of the oil, and this thing is oil cooled and lubricated without a pump. There's no pump. The oil is slung using this gear up into this oil tank, this reservoir.
Yeah. So you can see
and the reservoir has these highly engineered orifice sizes and channels to direct oil to all of the bearings and the gears, and this goes off to the rotor shaft to cool the rotor.
Yeah.
And so they've, without the expense of a
and weight of a pump.
Yeah, of a pump. They direct the oil just using the spinning of the gear to get that. And even in the casting, they had little oil catchers to hold oil so that if you go to the airport, park your car for a week, and you come back out, you still have lubricated bearings. It doesn't dry out. So all of this attention to detail and clever design. You mentioned that this kind of process was first used by Henry Ford.
Henry Ford, and that's what I was just going to say. Henry Ford was a genius with engines. And quite frankly, a lot of the things that we're seeing here are directly applicable to engines, like finding out how to make the resistance or capacity or whatever all exactly the same. Well, this is what you do in an engine. You have equal sized runners, equal length runners, so that you can get the best flow into the engine. This takes a lot of time and effort, and everything has to be exactly the same length. And the stoichiometrics, like the flow that you want through the engine, it all has to be tuned and tuned and tuned and tuned. And we've got programs that we can get halfway there or a long ways there. But at the end of the day, it's like a lot of analytical data that has to go into it to make this thing work. This is kind of like those two things: the airflow and the flow through the current through the
Stator,
the windings here. They're all kind of the same, but a little bit different. This, I'm getting all excited. That's the problem here. You see, this is like the best tuned turbocharged, supercharged engine you can get, because in those types of engines, I have to really be careful about what does the air flow in like, and how do I get rid of it so I can get the maximum amount of efficiency.
This is the analog for that in the electric motor business.
Exactly. Yeah. And this, you've all heard me talk about, okay, everybody thinks that, oh, if I got a bigger battery, then I can go farther. There are a whole bunch of things, there's 5 things, and I'm going to talk about 2 of them. One is friction. When I see this, I'm impressed. These bearings are to die for, and that's a fact. This kind of stuff, there's almost no friction here. This is amazingly good. I really like the way they've done this, and I can't stop talking about it. So anyhow, but friction here is one of the 5 things that makes things work out. It's not always throw bigger batteries at it. And a good example there would be the Hummer. I'm telling you what, these guys really did a good job. That gear ratio, I love it. I love the fact that they made a slightly bigger engine, or motor rather, even though it cost maybe a little bit more. And how they've controlled the purchasing agents. Hopefully they won't get the upper hand and screw things up. But everything here just.
And it continues with the rotor. So the rotor is, again, this is an 8-pole machine. It's a 48 slot. There's nothing super innovative about the electromagnetic design. It's very similar. Hyundai uses a similar one. Ford does. It's probably the most common electromagnetic design. Yeah. But it's the subtleties that make the difference. So here you can see the magnets form kind of a what we call a skew, that instead of all being in a straight line, the magnets have 4 steps. And from this step to this step is equal to 1 slot in the stator. And so what that does is it makes the noise that you get with each time a magnet passes one of these teeth, it hits it with a force, and the tooth vibrates, and you get a little bit of noise, acoustic noise. And by hitting the teeth with the noise for the force at different intervals, you spread that out. Instead of making a pure tone, it reduces the overall noise of the machine. So this is a detail. A lot of companies use this technique to do this. This isn't particularly unique to VW, but it's just one of the details that they put in to make sure that not only is it a powerful motor, but it's a quiet motor.
But at the end of the day, we usually see a much bigger gap, like a much bigger distance between here and here. These guys have somehow collapsed that a smidge, and so it's unique a little bit. I mean, everybody skews the steps. It has 4 steps or something.
It's common.
Yeah.
It is also, sometimes we see like a V pattern, so they balance that. So when you do it all in one direction, it can create an axial force. Yeah. But that's fine because they're using these tapered roller bearings in the
roller bearings,
in order to take up the So the bearings are designed to handle that extra force.
Yeah. By the way, one thing while we're talking, these are called angular contact bearings because what happens is as this is pushing into that, you want it to work at its optimal. So this force calculates which one of these bearings you're going to use, and as you load it, it becomes even better as far as friction is concerned.
Yeah.
The friction goes down when the load comes onto those.
Yeah. And of course, for this particular one on the lay shaft, it's due to the helical gears that are producing the axial load on this particular one. And the motor is acting through the input shaft. So that's the rotor. We got, in addition to the skewed magnets, they've chosen to go with stronger magnets. Again, it's a cost trade-off to try to get extra efficiency and this really high torque to give the customer that punch off the line. Yeah. And so the magnets are a choice to spend a little more money maybe, but give the customer a better motor.
Right. So these magnets are likely neodymium. We
Yeah.
haven't taken them apart yet, but we kind of know it. They'll be neodymium magnets. Everybody else is trying to use common magnets, ferrite magnets, with no added special ingredient. And if you're spinning up really fast, okay, fine. You got a dentist drill, like you were saying, and people will just put up with it, or maybe we'll put a blanket over the top of it when it gets into the engine. These guys are moving in the opposite direction and going with probably a superior magnet at a slower speed, which means you don't have noise in the in a cockpit, and with this gearbox, holy crap!
And you get more torque per amp, which is efficiency. That ends up, especially for light load, where it's not just punch off the line. It means that when you're driving in city traffic under normal circumstances, just putzing along, you're using less current. And so your battery lasts longer. So that's the real payoff for the stronger magnets. So all kinds of things that we love about this. We haven't even started talking about the inverter yet. We already did talk a little bit about the stator. I want to go into a little bit more detail on the stator. It is, as you mentioned, freeze fit or heat shrunk into the housing, which again requires tight tolerances on this inner housing and the outer housing so that everything fits together perfectly, because when you put it together with a heat shrunk fit, you only get one shot at it. It goes in and you're done, and if it didn't go in right, then you've got an expensive piece of scrap. And so it's highly automated, and everything has to be tightly controlled. When you see this kind of build quality, you just know when you walk into the plant, there are going to be statistical process control sheets with today's data on
last
them.
hour's data.
Yeah, last hour's data, showing that the process has I don't use nerd speak here, but a CPK of better than 2, which is engineering for a process that's really under control. Yeah. Highly tuned. That I have on here, it's a 48 slot 8-pole motor, and it does have 4 parallel paths, and again, very similar to that Ford Lightning. And one of the things I did mention about the Ford Lightning, and is true of this gives them a very easy upgrade path to 800 volts. So this has 4 parallel paths at 400 volts. All they have to do is go to 2 parallel paths by changing these connections, and you've got an 800 volt motor. And so they are, not only is it optimized at 400 volts for high efficiency, but they've left themselves an easy upgrade path to 800 volts should they choose to go that way in the future.
Well, everybody's going that way.
It does look that way.
We have to move to 800 volts. I mean,
the beauty of this is, again, it fits in the same package. It's a direct upgrade to the existing products they have, and expandable to the next generation.
Well, backward compatibility to me is a really big deal. We see this all the time on Tesla's stuff. They use the same stuff. It looks the same from the outside. You go inside and you go, that's totally different. But the outside characteristics don't look much different. Sometimes they'll thin out the walls or something like that, and they'll change the circuit boards, or they'll change the configuration that it got underneath. But that backward compatibility means I don't have to redesign.
Costs.
Exactly.
Yeah, it's just fantastic. So the huge savings in integration costs that you get by having that backwards compatibility, it's worth every penny that you put into the motor.
Yeah. Well, this is one of the things too that every engineer wants to have their stuff a little bit different, so that their thumbprint is on it and whatnot. So getting engineers to not do what they want, which is
make a little change
that buggers up everybody in the plant. But this is, I'm pretty.
All right.
Except for
yes, okay. VW does not get a complete pass.
No.
So we do have a few things that we think we could help out with. The inverter is it's a really nice package, and it's integrated in their previous design. The inverter was in its own aluminum box, and then they bolted the box on top of the motor.
housing, yeah.
And that leaves you with a connection. You have to make both fluid connections and electrical connections. All of that is extra cost. And so they have done a much better job of integrating the inverter into the housing of the drive unit. But they're doing this with an awful lot of threaded fasteners. So this aluminum frame, they call it the Spriter frame, it does perform the function of electromagnetic interference protection and maybe some cooling. But main function really is to support all of the power electronics. So here's the board for the controller, and underneath this is the capacitor inside that aluminum case. There is a cold plate that's inside here, and what we can't see underneath is the switches, the IGBTs. This is using ordinary silicon, IGBTs, which is typical for 400 volts, as opposed to the silicon carbide switches that people are going to at 800 volts, which have lower loss. So this whole thing just drops into the housing here. I kind of wanted to point out this, one of my favorite features is these little tubes that go in, and so the fluid connections are made kind of automatically as you drop it in to connect the cold plate of the inverter to the fluid flow of the rest of the motor. So first the fluid goes through the inverter, and then it goes off into the motor. So they did that with a nice little part. But yeah, they could really do with a few threaded fasteners for putting things together. There's just so many failure modes.
I really can't grasp the concept of why this is like it is. Now, and that's for 400 volts. Okay, so I could get rid of the problems associated with crosstalk and whatnot with a piece of tin foil for 400 volts. If I move it to 800 volts, and that's the only way they're going to get a buy here from me, then maybe this is needed, okay? But it's pretty thick, and I don't like, this is to me a useless bracket right now. And it's got a tremendous number of screws. I don't understand that either. This thing really doesn't see a lot of excitement. I don't know why. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 screws to hold down
the circuit board, 15 screws, and an additional dozen screws or so holding the aluminum plate down.
10. So you've got 10 or so bolts holding this thing together, and just I don't understand it, because quite frankly, we work on rocket ships, and I don't bolt the circuit boards down like this. As a matter of fact, most of the time they go click and they're done. I just use what do you call it? Circuit board
snap fits.
Yep. So this looks, I don't know, and to me, every time I'm running down a screw, I'm taking a chance at breaking that micarta because it does break. And what happens if the screw point jumps out and decides to take out one of these resistors or whatever? I mean, I don't know. Anyway, let's talk about these ferrites here.
Yeah, that is a little unusual. On an inverter, we don't usually see the use of planar transformers. And so there is some innovation here on the circuit board, and it is a nice package size overall. So there you get some kudos for that. And again, at the moment we're still in the process of the teardown. We're going to take this apart and get a look underneath and cost out the components to see how this stacks up. But yeah, there is some innovation here by the inverter maker. We just think that the assembly process for it could be refined.
Yeah. Do you want to talk about the Infineon thing here?
Well, it is an Infineon chip, and
it's much smaller.
You know, Infineon has been as a long time player in the power electronics industry.
Yeah.
They've been criticized for being overly costly. They've always been a technology leader. However, the new competitors in the field have really driven Infineon's prices down. And so it wouldn't surprise me if VW is getting a pretty decent quote from Infineon on this stuff, just because the competition has driven them right down to the bare bones.
Yeah. Well, it's always the same. Sooner or later, somebody's gonna.
They were the big dog, and originally, but the rise of the China-made power electronics has really put the screws on costs on these components.
Well, you know what? You get what you ask for. So Infineon went to China. Oh, you can get cheaper, blah, blah, blah. Well, it's good for a while. But and no matter what low-cost country you go to, eventually they're going to figure out more than you are because they're doing the manufacturing. Innovation comes from manufacturing. As soon as you don't manufacture, your innovation goes out the window. Oh, we have scientists. Yeah, okay, scientists all by themselves are interesting, but they do not give you what you want in the future. And that is, how do I make that chip smaller? How do I make it? That's where you start, right there. How do I make it? And doing it in a laboratory, that's interesting. Doing it in production rates of the billions like these things, that's where you find out what the future is. As soon as you give away manufacturing, and every consultant except for Munro Associates wants to tell you to send it to a low-cost country, send it out there, make bigger bucks, you'll get a bonus, blah, blah. It's all driven by stupidity. It's all driven by greed. If these guys would have just stuck it out here, made it themselves, didn't show anybody what they were doing, they'd still be on top of the planet. Nobody would be able to figure it out. You can take it apart and look at it, but you can't tell how it's made. If you can't tell how it's made, it doesn't matter. It doesn't matter if you can reverse engineer the design. How is it manufactured? How does it get in the industry?
That does lead into something I wanted to mention.
Yeah.
I forgot about. We want to talk about sourcing of these, but this is a true European motor.
Yep.
The sourcing, we're taking these apart, and the sourcing of the components are all over Europe. Germany, Hungary, Italy, Czech Republic. There's Turkey in some cases, but there's this is a true European motor. The content from Europe is all over the place, especially the parts that stand out from a build quality perspective. It's just not really a surprise that companies that historically do great work are doing great work with this. And so yes, this is Europe's entry into the electric vehicle market.
Germany hasn't been real exciting of late.
Frankly, VW has been taking it on the chin in the electric vehicle market. And this is going to make a huge difference.
It is, and I think I know that Rivian and VW have something going on. Maybe to get the volumes up and whatnot, maybe Rivian might want to check this out, because I'm pretty excited about this right here. This is a really good job, and it revitalizes my faith in, well, let me go not that far. I'm really impressed that VW cranked this out. I'd like to see a lot more coming out of VW, but man, I'm pretty happy about this. Last thought?
Yeah, well, that's what we have for you today. And so anytime we see fantastic engineering, engineers don't usually get a chance to be showcased. And when we do get showcased, it's usually because we screwed up.
Yeah.
So finally we get a chance to give people credit where credit is due in areas that typically might go unnoticed to the public.
So VW, this is the example. Now, basically, you need to talk to the rest of the engineers to come up with something that is equal to this stunning example of engineering prowess. Anyway, thanks for watching, and stay tuned for more Munro Live. Thank you. Bye.